product, you remember the output has to be vector, so you cannot use any dot operator here. It's all cross operator, A cross B cross C, where any bracket is anywhere between this and this or this and this, it doesn't matter, because ultimately you are getting another vector here and you are multiplying with this vector. So the triple product is output is a vector quantity, and this vector has to be perpendicular to A, B and C. See, let's go to the notebook where I can show you some of the stuffs. Let's begin a new chapter here, and this chapter name is vector triple product, and we are learning this vector triple product using this book. And as I told you, it has to be three vector quantities multiplied using cross product. It cannot be a dot product because you are getting a vector output. So you remember in the cross product, if there are two vectors, if there is a vector like this and if there is a vector like this, and you are doing the cross product, you will get a third vector which is perpendicular to both A and B. If this is A, this is B vector, then C vector will be perpendicular to both A and B. So if these two are in XY plane, this will be Z axis or parallel to Z plane. So if you try to see the triple product here, A cross B, B cross C, remember these are bold faced characters so that you know that these are vector quantities. So there are three vectors. First we'll consider B cross C. There is a vector called B here and a vector called C here. So you will get a vector which is multiplication of B and C and is parallel to B and C both. So if B and C are in XY plane, it is towards Z plane, Z axis. And now there is another vector called A. This is A. So when you multiply Z axis coordinate item with A, which is either in X or in Y, you will again get a vector which is in the same plane as B and C. So that is what they have discussed here. This vector is perpendicular to B and C, and so it lies on the plane of B and C. It lies on the same plane where B and C is there. But B is not parallel to C. If B is not parallel to C, if they are parallel, you will get sine 0, which will make this term 0. So if they are not parallel, you will get output as like this. Means I'm sorry. So if you have three vectors A, B and C, this is A, B and C, three vectors, B, C. So you will get A cross B cross C somewhere here, which has some scalar which is equal to some scalar multiplication with B vector plus some other scalar multiplied with C vector. So it's like few times of B and C, and it lies in the same plane, unlike the scalar triple product. And if Before discussing this part, let's see some of the things to make it easier. If I have a vector like, let's write it here, A cross B. Let us say I have two vectors that are multiplied. To make things easier, see, sometimes the book assume that you know some of the stuffs and they start writing. So you'll get a vector called C. Okay, now you know that A and B is perpendicular to C. C is always perpendicular to both A and B. Now let's try to multiply this term with either A or B in a dot product. What will happen? So that is my question. Let's see. You know, if you try to expand this term, say this is a vector quantity and this is a vector quantity, you will get a cos theta term. And since the cross product of A and B is perpendicular to both A and B, so the angle between A and the product is 90 degree, you will get a term called cos 90, which is 0. Okay, so if you are making a cross product and if you are trying to use any of the terms used in the cross product for dot operation, you will get a result 0. So same thing happened here. You were doing A cross B cross C, where B and C was inside a bracket, and these are boldface so that you know that these are vectors. And if you are trying to multiply this entire term with another quantity called A, like this, and do numbering. So you know that this term, bracketed term, this term will be perpendicular to both A and B cross C, and then you are making a dot product with A. So you know that angle between this vector and this vector is 90 degree, so this term will vanish. So that is what they have discussed here. If you multiply with A in dot product, the result will be 0. So let's not go into these details because these are of no use. We have to learn these things, how this works. So let's try to find out this. Okay, so for that probably we'll have to see the text here. You know, this is a 0, so that means the cross product was written earlier like this. So now if you are multiplying A dot here, you can write this term like this: x and y scalar quantity, so they can be taken out of bracket, and the dot product can be taken inside, and this term equal to 0. So you know that from here you know that x divided by A dot C equal to minus y divided by A dot B, and these are scalar quantities, so lambda can be assumed as the result of this thing. And you knew from here that A cross B cross C equal to xb, x time of B plus y time of C, that lies in the same plane as B and C. So you know x is lambda into AC, and y is minus lambda into AB. So you can put these things here. Lambda is common, B is this term, and x is expanded as AC, so BAC minus CAB. That is what you are getting here. So if you assume that lambda is 1, that is in practical it has to be 1, so you get this cross product as this thing. Let's try to prove lambda is 1. In a special case, when A vector equal to B vector, we will have, see this thing is expanded here, A cross C, since A is equal to B. So you will get the output as, since B will be going here, you will get AC minus A square C square, and by interchanging dot product you will get this. So if you expand it like this, you'll know that lambda has to be 1, and hence the cross product can be written as, this is a simple cross product rule, A cross B cross C equal to B A dot C minus C A dot B. So this is called back cab rule. BAC CAB, back cab. BAC CAB. It's easy to remember, and you will wonder that this is a cross product, so it's a vector quantity, and is it a vector quantity here on the right side? So let's see. A dot C is scalar, A dot B is scalar, and but they are multiplied with a vector quantity here. So these scalar quantities are basically x and y that we were discussing in the book. These x and y, these x and y. So basically you will get a vector here which is x time of B plus minus y time of C. So basically A cross B lies in the same plane, and it has a it can be represented as x times of B plus y times of C. So that is what we are getting in a vector triple product. So this is what we had to learn today, and in our next class probably we'll discuss some of the applications of actually I'm looking for some of the applications of vector difference, means vector triple product and scalar triple product, before we move to we are not going to discuss these things here, because these things will only increase the complexity. We'll jump to the del operator, but before that I want to show you some of the examples of vector and scalar triple product, so that it will be, you know, easy to remember for each of you, and then probably we'll discuss these things. So next times probably we will use different book where scalar triple product and vector triple product are extensively discussed. so that probably we can use them. For now, I would suggest you that you go through this book. This book, as you remember, is The Mathematical Methods for Physicists, a concise introduction. And we are learning this book since 7 or 8 days, and we are doing quite good. We have learned what are scalars and vectors, and then we went to the scalar product, vector additions, vector subtractions. We learned that vector division has nothing to do with 2 in mathematical physics. It doesn't make any sense. And then we went to the triple products that we learned today, and we saw some of the examples where we saw how to geometrically add vectors or mathematically add vectors and subtract vector. I believe that this is the time we need to solve some of the problems in mathematical physics using whatever we have learned, so that we'll recall each and everything. So I'll try to find out some of the tutorials or some of the problems that we can solve in our next class, and then we'll jump to the del operator, which is something that we must learn as soon as possible, because unless we learn del operator, we will not be able to go into some of the theorems of mathematical physics, and will not be able to understand the curvilinear coordinate systems, the polar coordinate system, the cylindrical coordinate systems. So this is how it will progress. If you have any comments or if you have any doubts, I would strongly suggest you to write to me, and you can probably go through my previous videos where I have used a very simple language to try to make you understand how mathematical operators work in physics. If you still have some doubts, you can write to me. If you have some comments or suggestions, you can still write to me. For now, thank you very much for attending my class, and goodbye.